We cannot start by not advertising AutoCube because we are here, so we need to. So this is one of the systems that we have that you cannot see because it sits underneath this thing. That is now a nice polarization resolve magnetoreflectance spectroscopy system that is fully automatized and ready to be used for measurements that I will not present today. Because, why should I present this? I actually want to really go back to the very beginning and show something very, very silly or very stupid, but maybe useful, and then lift the degree of stupidity a little bit throughout the talk, and then go very, very quick at the end so that Brian can sort of start his fantastic talk with everything that I would have said, not said. So we all know this story about graphene, that each layer of graphene absorbs 2.3%. That's a very, very old story, 2008. So the absorption of one monolayer, 2.3, two monolayers, 2.3 times 2, so 4.6. And then, then becomes complicated because you need to do times 3 times 4, and it's a complicated story. So the transmission, so it's kind of flat. There is a bump in the UV due to things that we're not going to discuss, due to the interaction with the M and K points of the Brillouin zone, but that's not really important. The important thing is the following. So, okay, each layer of graphene absorbs 2.3%. So if I put 10 layers, it will be 23%. 20 layers, it will be 46%. And then if I stick some silicon underneath the graphene, and I try to measure the Raman spectrum of the silicon, of course, the light has to go through the graphene, to the silicon, do the Raman thingy, come back, through the graphene again, so another, 40% that you lose, and basically there's nothing coming out. So, of course, if I have one layer of graphene on silicon, I have a nice Raman spectrum, and I have to really divide it by a large number because it's very intense, the Raman spectrum of silicon, sorry. But then with 28 layers, so 28 layers times 2 times 2.3%, it should be already significant. But then I get to 115 layers of graphene, and 115 times 2.3% times 2 should be something like 100% at least. So you should be seeing nothing. But you see a pretty decent spectrum of the silicon underneath. So you put 1 million layers of graphene and you still go through all of it and come back, which is kind of weird because you need to absorb 2.3% per layer. So something nice happens in the multi-layers of graphene, and also happens in the multi-layers of anything else, all the layered materials, that essentially these things act as natural optical cavities. And so the light goes and comes back, reflects at the interfaces and so on, to the point that the things that are usually assumed don't necessarily happen. So you have two ways of approaching this. One is basically almost like first-year university textbook. So you take graphene as a bulk, and you give a distance that is 0.3 nanometer for each sample. And the other option is that you consider them as made by individual planes, and each plane is separated by a certain distance. So that's the effective thickness approach. I'm not going to go and discuss the difference between the two, and of course, you need to give some sort of doping and some wavelength. But what is interesting to see is that the transmission is non-negligible up to almost 1,000 layers. And the absorption essentially peaks at less than 75%, even with 1,000 layers. So even with 1,000 layers of graphene, you don't get 100% absorption because of these cavity effects. So it's this natural optical cavity that is forming by having graphene. So you can actually plot it a little bit more explicitly. So there are a couple of approaches that I say, I'm not going to discuss the difference between red and blue. For the sake of this talk, let's say it's the same. But the one that is important is this 1 minus n times 2.3%, which when we I was one of the many people who published this stuff in 2007. There was the August of 2007, like 6 papers came out between APL and nanoletters, and we all gave a linear relationship, which is this one at the top. Then, of course, it becomes nonlinear, and of course, when n is 10, 20, 30, 40, it should go to 0. But it doesn't go to 0 up to several hundreds due to these effects that we have. The rest is pretty sort of standard optics, so for the sake of time, I will not go through it. I mean, once you know the trick, you do all the multi-layers, the light coming in and out, all the interfaces and so on. And of course, it does make a difference if your n layers of graphene sits in air, or if it sits on a substrate, and the substrate is SiO2 plus silicon and so on. So you can do this calculation, and of course, for 10 or 20, it happens exactly what you would expect. Interesting stuff happens when you have hundreds of layers of graphene, and again, I'm not going to go through the results. And of course, if it's supported, for example, on silicon oxide on silicon, the trends of the curves are different. So I spare this, but the theory is basically not even a theory, it's an analytical stuff you can do. What is quite interesting is then, let's consider the intensity of the G peak, for example. So the intensity of the G peak is not linear with the number of layers that you would expect. So the thicker the graphene, the more intense the G peak. But it has a very nonlinear behavior, and it, of course, changes with the wavelength. And the intensity can be 50 times larger for, like, 20 layers of graphene. Due to this cavity effect. So again, this is very, very sort of simple, super simple physics, but in first approximation is not intuitive, and then it's super intuitive. And then what, of course, is interesting, if we look at the intensity of the silicon peak, this goes to 0 after many hundreds of layers of graphene, and not after the immediate 10 or 20 layers as you would expect. And the theory matches very well the experiments. So there are n layers of graphene, and in fact, n layers of whatever layered material. They are free, given by nature, optical cavities. And once you know that, and you treat them as multi-layers in optical cavities and so on, you can use all the machinery of optical cavity to whatever you want. So there is modulation of transmission, absorptions, reflectance of the flakes, and you cannot just consider the linear absorption, as everybody naively thinks since 2008, and you have enhancement effects and so on, and you can simply use the transfer matrix approach to do these calculations. Anybody can do it. You can give this as an exercise to, like, a first-year PhD student just to get used to it, and it's a nice little exercise, and okay. Then let's do another step forward. So we discussed about the in-plane vibration. For many years, we've been discussing about the other signature of the multi-layers, the shear modes and the layer-breathing modes, that are the two modes that exist in whatever layers. I now go very quick because this is old stuff. So we have shown them many years ago, and they scale with the number of layers, unlike the G-peak. For example, MOS2, I always like this picture. This is very old, 2013, but we managed to have between 1 and 20 layers of MOS2, and you can see clearly the layer-breathing mode, the C modes or shear modes, and in fact, for n layers, there are n minus 1, but I didn't label all the small ones here. So completely well-known stuff. For 10 years, we published 1 million papers on this. And of course, it works for any layered material, so you don't need to know the symmetries and so on. It's very simple. So bismuth, telluride, celeride, gallium selenide, whatever. It's super easy. Niobium selenide, of course, is difficult because it reacts in air. So if you put it not in air, it works fine, and so on. So bottom line, what we showed a couple of years ago, is that all the layered materials, whatever they are, they can be MOS2 or HPN, graphene, you can do like in these jokes about physicists, that you can model all of them as a ball and a stick, and that's good enough. And you can do it really because it is good enough, the ball and the stick, because the in-plane interaction is so much bigger than the van der Waals interaction that the joke about the physics and the ball on the stick perfectly works here. So we have different point groups, different symmetry-based selection rules, different electronic properties, different electronic arrangements, but we have a similarity in the vibrations. So if we plot the C modes or the layered between modes for HPN, graphene, MOS2, whatever, you look at these lines, but they basically are one graph. They are all the same. And there is the simplest equation in the world that describes the position of any mode in any 2D material is sinus I pi divided 2n. I had a question from a theoretician telling me why there is an imaginary constant there. No, I is a number that goes between 1 to n minus 1, is not the imaginary constant. And they are just normalized to the parallel and perpendicular interactions between the planes. There are a couple of people here that I saw, maybe there are more than 2, who came from the nanotube field. And in nanotubes, we had these Kataura plots of the diameters of the tubes as a function of band gaps. It turns out you can do the same kind of plot of the frequency of these modes as a function of the number of layers, and we call them fan diagrams. And then you can probably want to go and look at all the possible frequency of all the possible existing and not existing layered materials. So there's about 5,000 of them. Then you group T. I don't know if you remember the paper of Porto. Many years ago, it was 233 pages of paper because there were like 200 pages of tables because he looked at all the possible groups and so on. So it turns out we did the same. I mean, we means some students and postdocs because it's kind of laborious. So it took some time, and then we convinced Paul Weiss to publish the worst paper in ACS Nano with a lot of tables like this, because I had in mind the Porto paper. I said, I want to do something similar. Of course, everybody says, oh, ACS Nano can only publish 3 figures, 5 pages, and so on. I mean, I get all the people. I have broken the rules in every single journal, not just in ACS Nano. I don't care how many figures and so on. It is so bad that even here I cannot read what is written there, because and that's what we realized that was not good enough. So we, together with Nicola Marzari, we did a website where you click on this link and you basically choose the material you want, and it does all the group theory for you, and it plots all the modes and so on, and all online. That's much better. And the link is on the paper. So yeah, the paper is wasting. Well, first, the paper is not paper anymore, so we don't waste paper. But there is also a nice link, and you just write down the material you like. Now, I need to say one thing and then another thing, and then maybe I can finish the talk. So the first little issue is the following. A typical Raman spectrum with a normal spectrometer that everybody has, let's say that I have a resolution of 1 or 2 centimeters minus 1, which is sort of reasonable. So if I have 3 layered materials, one is a bulk, one is thicker, and one is thinner. This is the kind of thing I never like on papers. Some of my collaborators, they like to write papers with larger, smaller, bigger, and then I read this stuff and I say, what does it actually mean? What does thicker and thinner mean? So is it 10, 20, 1 million layers? What does it mean? I understand bulk. So, but if the accuracy is 0.9, and you use the theory for this ball and stick theory, in the thinner region, a fit will give between 4 to bulk, and in the thicker region, read from 5 to bulk. So that's not really very good, okay? But on the other end, if you look, the spectra are actually different. Sure, we can do slightly better than that. So without boring you to death and skipping a few slides, it turns out that if you think very carefully about how the Raman instruments work, about the pixels and everything else, the truth is that the crappiest Raman that you can buy has in fact a much better resolution when it comes to these modes. And this is all published, but basically you can get a resolution that is typically 0.02 centimeters minus 1. And I skip, once you consider all the reasons for these things to happen. So let me skip this, and you can get this much bigger resolution, which then basically means that region 1 is 7, region 2 is 10 plus or minus 1, so we get a very good accuracy. And this is very useful looking at the layered within modes, because, for example, these are one layer MOS2 to one layer MOSC2, which will be my final part of the talk that I will not be able to give. And that's the one part where the AutoCube was used to do magnetoresonance and so on, and to study many interesting things about the interlayer excitons. But what I just want to say here is that if you don't see the layered within mode, it means that your heterostructure is crap. It's crap because there is some dirt in between the layers, and they are not properly interacting, which means that you are not going to see the interlayer exciton, because the poorer electron and poorer hole, and by the way, in our case, we're really talking about a poorer electron and a poorer hole, and no hybridization, because, but I will not show it there. While in sample B, where you see the layer within mode, you see very nicely the interlayer interaction and so on. So you need the low-frequency Raman spectra, Raman modes, are really the signature of this interaction. And then this is reflected in the interlayer excitons that you can actually see. Now, I need to take 2 minutes, and then I finish. How many minutes did I use? 15?
Less than 2.
What? I still have less than 2, but if I don't take questions, I can use the 2 minutes. So let anybody, the people don't have questions anyway. So let's finish this part, the one without the AutoCube, by considering, after you do all this group theory, you want to use it for some. The beauty is you do all the group theory, you publish, and you know for sure that based on group theory, you cannot possibly see certain symmetry because you have published nice papers that say so. And then, of course, 2 minutes afterwards, you stick the sample in the spectrometer, and you see both odd and even branch of the electron that should not be seen. And that's actually bad. But the good thing is that you only see it when the excitation energy matches one of the excitons. So if you're outside the excitons, the group theory works well. If you are in resonance with the exciton, I have a problem. Or is it an opportunity? Because I can write another paper. So, well, long story short, so because I don't have time, but just first, beautiful, you say, okay, beautiful Raman spectra. I've never seen something like that. You never saw them before. I saw once this time. So you can actually do all these measurements on different substrates, and you can look at the intensity of these branches that should not be seen by group theory, and they suddenly appear in certain circumstances. Then there is the boring part, which is the theory, but it all boils down to the fact that there is, yet again, an optical cavity forming, and maybe I have a simpler, essentially, slide later on. So if we are not in resonance with an exciton, basically everything that should happen, the dipole approximation works, the sort of 101 Raman theory, no problemo. But then when you are in resonance, then you have these individual electronic states that dominate the Raman intensity. We have coherence of electron-phonon coupling, and so on and so forth. And then all these interference effects that you get in the naturally multi-layer samples, they come into play. So, and let me skip all of this that you can more or less understand. I like this picture. It looks like a Christmas tree. And basically, you can do this calculation, and you can figure out that, again, because the multi-layers of layered materials are naturally happening optical cavities, the interference effects that happen and in interplay with electron-phonon coupling, and so on and so forth, it sort of gives all these beautiful effects in the Raman. But of course, this is not only limited to the Raman. It has many, many other implications. I will now skip all the rest, but I know that Brian is going to give a fantastic talk about this, so there's no point for me to say. Apart from the fact that the message is, do study multi-layers with many layers and look at them as, you can think about Purcell effect, you can think about many, many of these things, because they are naturally occurring cavities, and they have all these nice effects. And of course, if you want to enhance them, be in resonance with some interlayer, intralayer, exciton. Of course, you can do the moiré stuff, which I would have, but I have to skip. So I go to the end, and I thank everybody, in particular, Ping and Tang and Eleftheris Lidorikis for all the work that I've shown. And I still want to take a minute to say this. As of this week, we have started this Innovative Advanced Material Initiative. The name is IMI. You cannot be wrong if you say IMI, you know. I cannot be you, IMI. So how can it be different? So IMI, and this will be a new large initiative for all the innovative means 2D, but we cannot call them 2D for political reasons. And advanced means the boring stuff that is not 2D materials. So the EC asked us to do this marriage of, you know, not of forced marriage. Actually, they say that forced marriages have less divorce rate than a marriage out of love. So maybe this is going to work better as if we started from there. And this will invest hundreds of millions of euros in the next 10 years and will continue all the effort done by the Graphene Flagship in the past 10 years. It's super fresh. This is the first day where this is out. If you go to the QR code, the web page is the crappiest web page you will have ever seen. But in the next few weeks, information come out. But I don't have time to go into the details, but get in touch with me if you want to know about this. Okay, thank you. Mm-hmm.